Hello everyone, in this video we are continuing our learning from the book Cloud-Based Remote Sensing with Google Earth Engine. We are following A1.2 urban environments. This chapter is about the urban areas observations in Earth Engine. It shares the fundamentals and also says about the per pixel supervised image classification using Landsat 7. I must say this is a very beginner-friendly chapter compared to the previous chapters which we have gone through. I am myself aware about most of the things said in this chapter already. There are previous videos in the channel covering most of the things, but this chapter is more connected with the urban land cover, and the learned things from this chapter are applicable in any other land cover. And I want to go through the codes as quickly as possible, like I usually try to. So to start the first section of the codes, the first one opens with the idea of preparing the GIF or GIF image. Preparing the GIF image is an easy task in Earth Engine. We have the collection filtered with the geometry. So here we have the dataset, Landsat 8 as the dataset, and we have also filtered the cloud presence, which is less than 3. And this string cloud cover land is available or can be seen in the image metadata. And we also doing this dot filter date. So we have these two dates, 2010 to 2020. We set the parameters for the GIF image. Inside this curly bracket we provide the bands, so 3 bands, 4, 3 and 2, and for this particular Landsat 8 dataset, this has the SR at the beginning because this is the surface reflectance data. Sometimes this can be confusing while we don't apply this SR underscore. And then we have the minimum and maximum values. So we can see here something done, multiplication being done. So this is something that depends on the need of the visualization, but it certainly depends on the user's knowledge. So in this case, minimum and maximum values has been multiplied with some constants. And then we have the region. This is our area of interest. And then we have this frames per second. So in this case 15 frames per second. And this determines how the image is going to display itself, how fast or slow it is. And of course the format is going to be in the GIF. For rendering the GIF image, or to make this thing happen, we have this UI.thumbnail, and this takes the collection and the parameters for the image. So we can print this image in the console after running this, and from the chapter we are set that this is the airport somewhere in India, and this shows the time lapse of the construction of the airport. And this is pretty applicable in any location, maybe for observing the cropland change, building areas, or anything that can be shown within the Landsat 7. Just that it needs to be meaningful. The parameters can be changed for different results, such as using different bands, using different frames per second, So this is the very first section of the code, and this chapter shares us this very nice way of making this GIF image. And the chapter also says the idea of the landcover dataset, the dataset that are already available in the Earth Engine. And the popular one is the MODIS-based landcover dataset at 500 meter resolution. This covers the whole world. In this example, the point has been set. So somewhere, I think, in Africa. So this particular example is related to Ghana. In this example, we have this MODIS land cover from which we are selecting this band LC_type 1. So this MODIS land cover dataset has different land covers. Among them, this has been selected, and then we are providing this image visualization parameters. And here we have the minimum and maximum value. The first minimum value is 1 and the maximum is 17. So this is the land cover dataset, and land cover dataset has these discrete values, each value representing the class, and for each class different colors are provided, and this is added as the layer by map.addLayer. So the primary advantage of such dataset for the users is the quick visualization to get the general idea of the change. We do not need to create the new land cover as this has already been created by the scientists, and the land cover datasets are tried to be made as scientific or as accurate as possible, and this such kinds of land cover dataset goes huge amount of testing and validating. So these are very accurate. So here this is continued by selecting for some dates. So here we are filtering this MODIS land cover based on the dates. So this is for 2019. Then after we are selecting this value 13. So this class value is related to the urban class. So this is for the year 2019. And then we have this dot mask to include only those urban pixels. So this is also repeated for the year 2001. So both of the layers are displayed. So the main thing to notice here is the different colors. For 2019, here some colors provided, and for 2001, different colors provided. Once we run this, we see the magic here. So the first layer is the land cover of this area. So we can see very bright colors, different colors representing different class values. So if we see MODIS urban 2019, so this is the urban layer for the year 2019 of this area. And if we do this again, MODIS urban 2001, the magic is that there are two different colors. So the first one is the 2001 and the second one is 2019. So what we are seeing is the increase in the urban layer, or the increase in the urban areas. So this is very nice way to display or nice way to represent that there has been increase in the urban area in this particular location. Same methods using the other dataset. So this one is called the Corine land cover. this is only made for Europe. The land cover has the single class further being divided into the multiple classes. We can see this here. So we have different class values. Artificial surface here, artificial surface. So there are multiple classes with the same name but different properties or different description within them. So here, for example, we are selecting the values less than 133. So anything less than 133 represents the urban areas in this particular data set. So before that, we are setting this at setting the map somewhere here, somewhere in this location with the zoom point 10. Then we are selecting this land cover. This is the band of this land cover data set. We then filter it by the dates, and here again the color is provided for the year 2018. Similar thing has been done for the year 2000, and some color has been provided. A different color has been provided, and once we run this, we get the same thing as we saw earlier. So this is for the 2018, and this is in red, and then we see the grayish color that is in 2020, and anything that appears red is the urban area that has expanded or that is new compared to 2000, and this is how we see the change. So this is just the visual representation of the increase in urban area. The other example is for the USA. There is this land cover dataset especially made for the USA called the USGS National Land Cover Database. And so here in this particular example, the land cover is selected for the year 2016. This is clipped with the area of interest here. So value 24 is selected. So this value is related with the urban areas in this particular data set, and then we can display this as the layer. So the new thing provided in this section of code is the calculation of the area. So the image is multiplied by this function here, ee.image.pixel.area, and reduced by dot reduce region, and inside this dot reduce region we have reducer ee.reducer.sum as the reducer, and geometry as our interested area. And then we also have the scale, and after doing this we can print the area in the console. So this is only for the single class. So there is a helpful block for doing the area calculation in earthengine, but here this particular example is showing us the way to calculate only the area of the single class. So if we run this, we get some values here. So this is in the meter square. This can be converted into the kilometer square as well if we need. So in the layers, the first one is the land cover data set, and the second one is the whitest appearing colors. So this is the urban area in this particular location. So this is the data set of the USA. Then the book chapter tries to share the idea of the image classification. So let's quickly go through this. This starts with the function as always, and in every case the cloud masking function using the quality band. Within the function some operations are done, multiplication and additions are being done. So this is to apply some factors or the scale factors for the bands. So this example uses Landsat 7. The image has been filtered in this case from the year 2020. So this is for the year 2020, and then the function has been mapped, that cloud masking function, and this dot median here gives us the single image. So this will reduce any clouds. So this will be the image that is very clear with no clouds, no outliers. And this image can be added as the layer. So it is not appearing at the moment. Let's run this again. Anyway, let's move ahead. For the classification, we need training points. So the two different feature collections are prepared in this case. The first one is the BU, meaning built up, and the second one is NBU, meaning not built up. So just the notations to know or to make it easier. So these are made with a careful consideration with observation of the high resolution images, and the geometry has the ways to make this feature collection. We can provide the name, we can select to make this as feature as well, or the feature collection, or the geometry. By default it stands at the geometry. The collection of the geometry or the collection of the features can be the feature collection, and different properties can be added to this feature collection. And here this two different feature collection has been made into the big feature collection. So both the feature collection has been merged, and the name has been given as LC. So the popular machine learning algorithm is the random forest. So random forest is applied in this example as well. So random forest is done by ee.classifier.smile random forest. For this algorithm, the needed parameter is the number of trees. So here the number of trees are provided as 20. So the training is provided to the algorithm, and the class properties are the class, and the input properties are set as the bands. So here we have the list of the bands. Here we have the training. So from the image we are selecting the bands. Inside the sample regions we have this feature collection, that big feature collection, and our important properties is the class to represent whether that area or that point is urban or not, and the scale value as 30. And then we have this ee.classifier.smile random forest, inside which we are providing the number of trees, and we are training this by the features. We are also providing the class property and the input properties, and in the comments we see the use of each parameter. So for example, this class property is the class that we want to predict. This input properties are the bands the classifier will use for training classification, and this is how we train the random forest classifier. So we can apply this for the image, and once you apply this to the image, the result can be added as the layer. So if you run this, so one new thing we learned here was that if we don't provide the class value here, the final image classification will result in only the single class. So I think this might be the trick that can be applied if the number of classes is 2 and if we're interested in only one class. So I think we need to check this if we want to apply this in the 2 classes and we only want the single class from that classification. So to continue, this has been further applied or repeated for the year 2010, and the subtraction between 2010 and 2020 has been done. So 2 different classified images, something like the manual subtraction of the numbers has been done. So 2 images, so 2020 image is subtracting this 2010 image, and from this the resulting is the difference image, and again this difference image can be added as the layer, and this different image is the image that shows the increase in urban land. And again, this is something similar to the previous examples that were done in the landcover dataset, but the difference here is that we trained the classifier, we got the 2 different classified images, and from that 2 classified image we subtracted, and the subtracted layer or the difference layer is that area where the urban area has increased. And this is the overview of the chapter, and this is a very learner friendly chapter. The concepts are applicable to other landcover as well. I would like to thank the authors for this very nice chapter, and also the viewers who watched till the end. In the coming days we will together follow the chapters, and please particularly follow this A1.2. This is a very nice chapter, and I would say this much in this video. So thank you for watching.